So guys, today we're going to start actually studying electrical circuits. So if we have a circuit and we need to find out what is the power consumed in each element in the circuit, or what is the current that's flowing in each element in the circuit, then that's the topic of today's chapter. And actually so far we have studied how to connect two capacitors or more together. We studied how to connect two resistors or more together, but we never studied how to connect capacitor to a resistor together. And today this is also the topic of that chapter. We'll start this chapter by talking about Kirchhoff's laws, and we'll actually talk about Kirchhoff's laws. Today we're going to talk about DC circuit resistors. When we talk about DC circuit, I will tell you what does DC mean in a minute. Resistors, what's included under DC circuit is connection of resistors in series and parallel, and we have studied that already. Kirchhoff's current law, and we'll talk about that. We'll talk also about Kirchhoff's voltage law. Then we'll talk about non-ideal batteries. What does non-ideal battery mean? And we'll talk a little bit about power, and we took last lecture as well as about power. And at the end of this chapter, we're going to talk about how to connect a resistor and a capacitor together, and how to calculate the charge on the capacitor at any time and the current that's flowing in the on the resistor at any time. So this is the main topics in this chapter. DC current. DC current stands for direct current, and direct current means that the current is flowing always in one direction, and the magnitude of the current does not change. If the magnitude of the current does not change, and if it's flowing always in one direction, we call that a direct current. Current flows because we have a potential difference. Without a potential difference, we will not be able to have current flowing in a circuit. The battery, any battery in a circuit, is known to be the source of the electromotive force. It's a source of potential, only a source of potential. What is electromotive force? Electromotive force, it's the maximum potential, maximum voltage that you can draw from a battery. Between any terminal of battery, there is a potential. The maximum potential you can get from that battery, we call the electromotive force. And the maximum potential we get from the battery, it happens when we have an ideal battery. And when I say ideal battery, I mean the battery, the internal resistance of the battery is zero. Any battery has a resistance inside it. And if the internal resistance of the battery is zero, then the voltage across the two terminals of the battery is called the electromotive force. So in reality, do we have a battery that has zero internal resistance? The answer is no. No. So, but in here we're going to study, in our assumption all the time, we're going to assume that we have an ideal battery.
So if we have internal resistance,
I'll show you how to calculate.
so I mean we call the voltage EMF?
No, we call the voltage across the battery, across the terminals. So we call the voltage across the two terminals if we have an internal resistance. But if the internal resistance is zero, we call it an electromotive force. So this is a battery. We all know the shape of the battery. And if you connect it to a load, electrical load, a resistor, any device will be an electrical load. So this is a simple device. We'll connect it to a resistor. So this is the battery has a positive terminal and a negative terminal. The positive terminal is usually has a high potential than the negative terminal, and there is inside the battery an internal resistance. So if we look at the schematic diagram of the battery, what's inside the battery? That's inside the whole battery. We have an ideal battery that produces an electromotive force and an internal resistance. And if you connect that battery, the two terminals of the battery, to a load, to resistor R, then we call that a circuit. Now, the potential difference across A and B, across that point, between A and B, that delta V, the potential difference between the two terminals of the battery, will equal to the electromotive force minus the drop in the potential in the internal resistance. Any resistance cause a drop in the potential. So if we need to talk about electromotive force, this is the electromotive force. But what we measure in reality is the potential difference between the two terminals of the battery, and that potential difference that's equal to the electromotive force minus IR. If you look at that equation, the potential that you can get from any battery depends on the current that you can draw from that battery. So if you draw less current, zero current, if you draw zero current, then the potential difference will equal to the electromotive force. If you increase the amount of the current that you draw from the battery, then the potential, the maximum potential that you can draw from the battery will get less and less.
Doctor, why do we put a resistor inside the battery?
We did not put a resistor inside the battery. Any battery comes with its internal resistance. We call it R small. Okay?
Even internally.
All the components inside the battery, in the resistance of the terminals, all those chemical reactions that happen inside the battery that increase the internal resistance of the battery, that cause a resistance, as if you have a resistance inside the battery. And this is different from a battery to another.
مش المفروض ان في بيس ما بين التو terminals بتاع الباتري اللي هو increase the conductivity بتاعها يبقى ازاي بقى في resistance؟
Oh, the terminal itself is a metal, and the metal has a resistance. Any metal has a resistance. So if you measure the electromotive force across this, or the potential difference across the two terminals, you have to take that into consideration. And this is called the internal resistance of the battery. And it's different from a battery to another, even for the same manufacturer. طارق first.
If we need more electricity, we need...
What do you mean by electricity? Potential or current?
This is my question.
Or power?
The power.
Power. Then
We need more current or more potential?
this is the last thing that we're going to talk about in this lecture. Omar, listen.
Do I neglect the resistance of the wire itself?
Yes, Omar is saying, I neglect those resistance of those wires? Yes, we assume that those wires has a very, very small resistance compared to the load. That's why we ignore them. Okay, so from now on, we're going to ignore the resistance inside the wire. And sometimes I'll tell you that you have an ideal battery. So you're going to assume that R internal is zero. Yes, Omar.
The EMF of the battery outcome is, for example, 12 volts.
12 volts.
Then due to the internal resistance,
Then what you get?
coming out is less than 12
Yes.
volts. 11 point.
Yes, 11, 10, anything less than 12. Okay? So according to that equation, the EMF is considered as the potential across the battery if you have an open circuit, if you do not connect anything in here. And if you do not connect any resistor in here, then the current you draw from that circuit is zero. Then the EMF will equal to the potential across the battery. So if you measure the potential across the battery with a voltmeter that has a very, very small resistance, very, very small load, then what you measure by the voltmeter is the electromotive force. Power. Last time we talked about power. Definition of power. Power is the current times the potential difference. And the power that comes out from the battery, it's the current times the electromotive force. So it's I times E, it's I squared times R, which is the load, plus I squared times the internal resistance. This is the power that you can draw from any battery. Kirchhoff's law. Now, knowing what is the battery, from now on I'm going to assume that I have an ideal battery. All those batteries that you're going to see in the circuit that I'm going to show it to you from now on are ideal batteries. That means they have zero internal resistance. Yes?
In the previous slide, we assumed that the battery are ideal.
Yes. Actually, no. I did not assume that the battery is ideal, but I said that this is the E. E is the potential difference that's measured when we have an open circuit, when we have R equal to zero.
Doctor, what's I squared with R?
Oh, electromotive force, the electromotive force is equal to I times R plus I times R small. Kirchhoff's law. We have two Kirchhoff's laws. One of them that says, that's named Kirchhoff's voltage law, and from now on I'm going to call it KVL, and KVL stands for Kirchhoff's voltage law. Kirchhoff's voltage law says that the sum of the potential, if you add all the potential around a closed loop, the sum of those potential will equal to 0. This is the conservation of energy law. This, if you assume that the current flows in that circuit is I, then the energy, if I say energy, guys, or power, I'll talk about power. Power is the energy per unit time. So if we were talking about the same time, then the power here, plus the power consumed in here, plus the power here, plus the power here, equals to 0. The power N will equal to the power out. And this is the conservation of energy that we have talked about even in Physics 111. Energy N will equal to energy out. That's in heat, when we talked about in chapter 20 in heat, or mechanical energy in chapter 7 and 8. This is the conservation of energy. Again, in electricity and magnetism, conservation of energy is still valid. So Kirchhoff's voltage law is nothing but the conservation of energy. What I'm telling you, if those two batteries put energy in, those two resistors will consume them. Energy N will equal to energy out. And if you take I as a common factor, you take I out, that means that I times V plus I times V plus I times V plus I times V, and when I say V, they are not the same V. I times the potential across the battery plus I times the potential across the resistor, number 1, plus I times the resistor, the potential across the resistor, number 2, plus I, same current, so always the same current. I times the potential across E2, if you add all of those together, you get 0. So if you take I as a common factor, you end up by having this equation. Sum of the potential around that loop will equal to 0. A loop. It's a loop. So we'll study a circuit that has more than one loop in a minute. So for a single loop, this is a loop. For a single loop, if you add all the potential, you end up by having they add up to 0. And this is the conservation of energy law. Abdullah?
السيركت ازاي شغال اصلا؟
What do you mean?
الباتريز
Oh, this is something I will think about it later. We'll talk about it later. We'll talk about that later. Yes. Amr? Okay, Abdullah is saying, well, you have the terminals here. This is the positive terminal and this is the positive terminal. If the current goes out from the positive terminal, then the current is going to go out from that, and the current is going to go out from that, and how the how the current will flow. This is a good question in here. The higher the battery that has high potential will force the current to move in its direction. So that current will overcome that current, and you have a total current I flowing in that circuit. That I is not the I that's drawn from that battery, it's the resultant I. Okay? Okay?
resultant I equals the difference between the current coming from
Yes.
the first one.
Yes. Okay? So, this is the battery. We're going to apply few rules to apply Kirchhoff voltage law. We have to have those rules in mind when we go and apply Kirchhoff's voltage law. Again, Kirchhoff's voltage law, KVL, says sum of the potential will equal to 0. This is Kirchhoff's voltage law. Kirchhoff said that if you have to choose a direction, and in that circuit you have to go either clockwise or counterclockwise. Which one should I choose? It's up to you. Unless it's stated by an arrow in the problem itself. So which direction should I choose? Doesn't matter. So in this now on the screen you have, I have chosen the direction of clockwise. And I will do it by that direction. Then I will change the direction, and I will do it again by choosing the direction to be counterclockwise, and we'll see what happens. Okay, clockwise. So this is first thing, we have to choose direction. First thing that we have to choose a direction. Second thing is, every time you cross a battery, and if you go from negative terminal to a positive terminal, you take the sign of the last terminal. So if you cross the battery that way, then that battery has a potential of plus E1. If you cross it that way, then this battery has a potential of minus E1. It's the sign of the last terminal. So I'm going to go clockwise. I'm going to start from that point. Someone will say, why do you start from that point? Can we start from here? Yes, it's the same thing. You can start wherever you want. You're going to go around that whole loop, so it doesn't matter where you start. So I'm going to start from that point. I'm going to go that direction. So when I cross that battery, the last terminal has a positive potential. That's positive E1. Then plus, this is below, plus the potential across R1. Every time you see a resistor, there's a drop in the potential. And drop in the potential, that means that the power here is going to be negative. So this is going to consume energy. Consuming energy, that means that's negative energy. So this here will have a drop in the potential. I will call it minus. It's minus because there is a drop in the potential, and the potential, according to Ohm's law, is equal to the current flows in that resistor times R1. Then, if we continue, you get another resistor. There will be another drop in the potential. And that drop in the potential will equal to, this is the summation again, negative I R2. Then, because that battery, the last terminal is negative, then you get plus negative E2. All of that, if you add all of that together, this should sum up to 0. Now, look at that equation. If we know the values of E1, E2, R1, and R2, we can get the value of the current. This is obviously this equation. That equation is one equation in how many unknowns? 1, 2, 3, 4, 5 unknowns. We have to know 4 of them in order to solve it. Otherwise, we cannot solve it. So if you get a problem like this, I have to give you the values of 4 of those unknowns, whatever those 4 are. Okay, guys? So that's simple. That's now we know how to apply Kirchhoff's voltage law. What does depend on the circuit? Of course, this is different from the circuit to another. Of course. This is not a general equation. This applies only for that circuit. I promised you that I'm going to do this clockwise and counterclockwise. So let's do it counterclockwise. I'll start from that point. I'll go that way. And so I will choose this to be my direction, counterclockwise. So that arrow is reversed. I'll say. No. I'll say. It doesn't matter which direction I choose. Then I will tell you what's the difference between them. So I'll start from that E2. So you get positive E2. Right? Positive E2. Then a potential drop across R2. Then you get negative I R2. Then you get negative I R1. Then you get negative E1. That should equal to 0. Those two equations are correct. The two of them are correct. But if you solve them, one of them will, if you solve them for the current, let's assume that we know everything but the current. One of them will give you a current that's positive. and one of them will give you the same magnitude of the current. If this gives you 2 amperes, this will give you also 2 amperes, but it's negative 2 amperes. What does that mean? The one that has a positive sign means that you have correctly chosen the direction of your current. The one that has a negative sign, that means that you have assumed the direction of the current wrongly, and you do not have to repeat the problem. You have to mention that the direction of the current is actually opposite to what you have mentioned on the drawing. That's all. And back to Kareem's question, the higher the battery, then the higher the potential. That means that this will force the direction of the current. So this E1 is 5 volts and E2 is 3 volts, this will be the direction of the current. If E1 is 2 volts and E2 is 5 volts, this will be the direction of the current. But you do not have to memorize this, because if you just stick to the equation and solve it, you get the answer. If you assume any direction, doesn't matter, you just assume any direction. And if your answer is positive, then you assume the right direction. If your answer is negative, then your direction actually was not assumed correctly.
The higher potential, the higher battery potential.
Yes.
Will force the I to be in
its direction.
Even if I1 is less than I2?
It cannot be. It cannot be. This is a series connection. I in the circuit is the same. The current in the loop is the same.
I mean the current from each battery.
Wow, but we're talking, yeah, it cannot be. Lower potential will produce less current in a way.
Doctor, in circuits we always assume that current flow from positive to negative, but in reality it's the other way around.
Yeah, yes. Actually what happens is not, the current is the flow of electrons. So the electrons is flowing in that direction, and we assume the current is flowing in the opposite direction.
دول بقى البوزيتيف will give me the right.
There is nothing called right. This is the direction of the current, then this will be the direction of the electrons.
So this will give me the direction of the current or the direction of electrons?
It's the direction of the current. Okay, so another loop. Guys, in this loop, I have made 2 mistakes. I applied Kirchhoff's voltage law, and I want you to find out where are those 2 mistakes. I want to start with the Shadi actually. So then Amir Hosni. I want you to notice that I have specified the direction of the current. So I have specified the direction of this loop. We're going to go counterclockwise. So we're going to go counterclockwise. Keep that in mind. Nina, you're late. Shadi. So, where is my mistake? Amir, where is my mistake? Amir. Of course I do not do any mistakes. Come on, guys. You're right, I don't have a mistake in that equation. There's nothing, there is no mistake in the diagram nor the equation actually. And if you find one, please tell me about it, and I will discuss it with you to prove you, to find at least where is your misconception. Bishoy. No, the circuit is okay. The circuit is okay. So what I did is I started from that point, A. I start from A, point A. I'm going to go counterclockwise. So when I cross that R1, there is a drop in the potential. That's why it's negative. When I cross R2, there is another drop in the potential. That's why you have a negative IR2. When you cross the battery E2, the last terminal is negative. That's why you have a negative E2. When you cross R3, there is another drop in the potential. That's negative IR3. When you cross R4, then there is another drop in the potential. That's negative IR4. Then when you cross E1 to go back to the point A where I started, then you get positive E1. The equation is correct. This is the application of Kirchhoff's voltage law. Of course, this is a simple one-loop circuit. Yes.
Is there a problem to start with E1 and write the E1 in front of the equation, the beginning of the equation? So I must start from the resistor.
Ram is saying, do I have to start from point A?
So I either have to start with E1 or should I start like with...
You can start from any point in the circuit, any point, but you have to go one complete cycle around that circuit. Any point, okay? So I choose to start from point A. You can choose to start from point B and go that direction. So, if you look at that equation, if you took I as a common factor from all of those and move E to the other side, then you can calculate I. Assuming that we know the values of E1, E2, and the 4 resistors. This is one equation and 5 unknowns, 7 unknowns. One equation, 7 unknowns, and you cannot solve that unless you know 6 of them. If you know 6 of those unknowns, you can solve for the 7th one. Okay, guys, that seems easy. It's complicated. Let's complicate that a little bit. You have a circuit. That's the circuit you see. It has 2 resistors, R and R. Each one of them has a value of R. It has 2 batteries, 12 and 12. 3 batteries, 12. And a switch. That thing there is switch. So you start the circuit that way. This is your circuit. The switch is open. And the switch is open means that that battery is not part of the circuit. It does not do anything to the circuit. Then, after a while, then after a while you switch that switch on. You put it on. And I asked you guys what will be the current in that resistor before and after I switch that switch on. Before, I call it I0. After, I'm going to call it I1. So the current after I switch the switch on is less than the current before I switch the switch on. The current after I switch the switch on equals to the current before I switch the switch on, or the current after I switch the switch on more than the current before I switch the switch on. Again, the current in that resistor, the lower one. What to do? Look at the circuit. Obviously, we have one loop circuit. Before we switch the switch on, we have one loop circuit. This is the loop. This is the circuit actually. Twelve R volts. Which direction should I choose? Counterclockwise or clockwise? Doesn't matter. Doesn't matter. And that current is going to be I. So, what? Excuse me? Oh, you're applying Kirchhoff's voltage law already, right? Yeah. I'm a little bit slower than you, so guys, we need to calculate the current in this resistor. So I'm going to apply Kirchhoff's voltage law, and I'm going to start from any point. That point. 12 volts, negative, minus 12 volts, another negative, negative, I times R, negative, I times R equals to 0. That means that minus 24 minus 2IR equals to 0. That means that I equal to 12 over R, negative. What does the negative mean? My assumption was wrong for the direction of the current. You're right. And I did that intentionally to show you that there is no problem in that. There is no problem in choosing the wrong direction. You will find out that you have chosen the wrong direction at the end, so do not worry about that. So this is the current, 12 over R. This before we connect the switch on. After we switch the switch on, I'm going to draw only the small loop. The small loop. 12R. This is the small loop after I connect, after I put the switch on. Okay, guys? So in that loop, which direction should we choose? Okay. That doesn't matter. So I'm going to start from that point. Negative 12, negative IR, I1. I'm going to call this is I0 to match actually the slides. I'm going to call that I1. So in that case, I1 will equal to 12 over R, negative, again. No. You assume that the current in that loop is I1. Oh, wait. I didn't answer Ala yet. I did not satisfy him yet. Shadi. Excuse me? Can you move a little bit closer? It will save my time instead of repeating the whole thing again. Any place you want? Just they will give you a space. Guys, can you give to Shadi a space, please? Okay, Ala, when I choose a loop, I assume that in this loop there is a net current flowing in that loop is I. That net current is the contribution of all the components in the whole circuit. And I do not analyze what is each battery is giving to that resistor. I say that the net current in that loop, I'm going to call it I1. And that's the loop by itself, I1. I1 is the net current that results from the two batteries. The three batteries actually.
I think I1 is equal to I0. I1 is equal to I0.
Okay, so no. In the first, the current that guys. Okay, in the first loop, before I switch on, the current in the upper resistor and the lower one is the same. It's I1. It's I0. And after I switch the switch on, the current in the upper resistor and the lower one is different. Okay, and my question was to concentrate only on to compare the current between on the lower resistor before and after I switch the switch on. No, for circuit, the whole circuit, it's two. You have two currents now. After you switch the switch on, you have two currents. Current that flows in the R, and another one that flows in the lower R. Those are two different currents. There is no current that flows in the whole circuit. It's not the same current everywhere. Okay? Okay? Hussein first. Yes. Yes. Excuse me? Yeah, we'll get to that in a minute. We'll get to that in a minute. We'll get to Kirchhoff's current law in a minute. Yes. The answer is yes. Okay. How come?
انت تجمع الكرنت اللي جاي من فوق مع اللي جاي من هنا وهيعدي
لا فرق
ايه اللي بيخش دي تخش لوحدها
Okay. The current actually, and you're assuming that the current that goes from here, all of it will flow down. All of it will. You're assuming that all of it will flow down. Actually, it's gonna. Okay, guys. This is Kirchhoff current law. I will go to that in a minute. But now, to analyze that circuit, we have to concentrate on a loop. So when I applied, before I switch the switch on, obviously I have only one loop. That's not a problem. Before I switch the switch on, after I put the switch on, I have two loops. I can choose that loop to solve the problem, and I can choose that loop to solve the problem. Okay, I cannot, for now, I cannot choose that loop because I did not introduce to you Kirchhoff's current law yet. So I have to choose that one, that simple one, then to solve the problem, and you get the same answer. So give me a minute, then we'll introduce Kirchhoff's current law and we'll solve the problem again. And you get exactly the same answer again. Abdullah.
مش اصلا قبل ما اللوب بتاع الشمال دي تتحط before we put it. This one, when we put it on, it opposes the current flow from these other two on that resistor. يبقى الفولتج هيقل on that resistor.
No, for those values, 12, 12, and 12, the current is going to be the same. But if you change the values, the current is going to be different. I specifically have chosen those three values to show you that I can use that simple circuit, that one alone, to solve the problem. Now let me introduce to you Kirchhoff's current law, then we'll solve the problem again. Sorry.
We can use only this clockwise or anti-clockwise. دي لوحديها خالص ودي لوحديها خالص.
Yeah. Yes.
عشان they're separate loops.
Yes. 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 Yes.
We assume
No.
مش الكرنت في الارش في السكند ريزستور.
The current in the lower resistor.
And the lower resistor will be half of the first.
Why it's half? Why it's half?
Because here when the current of the 212 volts.
Yeah. Then you're talking about dividing the current. That's Kirchhoff's current law, and you're not giving me the chance to go to it. So you just keep your question about dividing the current till I go to Kirchhoff's current law, then we'll answer that.
We're dividing the current or حاجة بس like this one, the current from the left battery opposes the current from the فطبيعي
That's again Kirchhoff's current law. He's assuming something that's not true. It's not opposing. It's going to be at that junction. At any junction, the current gets divided. It's the same that like water flows in canals. If you have a big canal and then you have a junction and that two smaller ones. The total current is going to be divided into two currents, I1 and I2, at any junction, in such a way that the total current will equal to I1 and I2, and this is the conservation of charges. Okay, so that's a circuit. So in this is two-loop circuit. Two-loop circuit. Loop number one, simple one, and another simple one, that's loop number two. Then what happens? What happens is this. In what direction will the current flow? So I'm going to assume that actually the current will go out from E1 regardless of the value I know. Guys will tell me, but if E1 is less than E2, then the current will go out from E2 regardless of that. I'm going to assume that the current is going to go out from one of the two batteries. This is not the current that goes out from the battery. It's the net current. That's the net current. And this branch, I call that branch. I call that loop. I call this junction. I call that junction. So the current will go out, the net current in a branch, I will call it I1. I1 is going to flow, obviously it's going to flow in here. This is I1. At that junction, what's going to happen to I1? Omar, it's going to be divided into two currents, I2 and I3. I3 is going to flow in this branch, down to that branch, down to that branch, and at that point, it's going to meet I2 again, and they will combine to be again I1 will go back to the battery. This is what happens.
So I2 here is bigger than I3 now.
I don't care. I don't care if I2 is more than I3. We will find that out. So applying at any junction, what I'm saying at any junction, if you add the currents at any junction, they should be added up to 0. At that junction up there, I1 plus I2 plus I3 should equal to 0. Or in other way, I1 is going to be divided into I2 plus and I3. That means that I1 equal to I2 plus I3. So that's Kirchhoff's current law. Let's take example for that.
This is I1 plus I2 plus I3 equals 0?
Yes.
With different signs anyway.
Of course. If you solve that equation, you have to get one of them equal to the other two. And obviously in that case, I1 will equal to I2 plus I3. So how many loops do we really have in this circuit? 3. Loop number 1, loop number 2, and the big one, loop number 3. I'm going to ignore that branch when I talk about loop number 3. So I will apply Kirchhoff's laws on that circuit. Loop number 1, I will apply on it Kirchhoff's voltage law. Loop number 2, I will apply on it Kirchhoff's voltage law. Loop number 1, loop number 2, Kirchhoff's voltage law. And at a junction, I will apply Kirchhoff's current law. Then I will get 3 equations. And those 3 equations will have 3 unknowns. Obviously, those 3 unknowns, in that example, that's I1, I2, and I3. If you solve those 3 equations simultaneously, you will get the values of I1 and I2 and I3. And if you assume the direction of the current, I2 for example, to be downward, and when you solve the equation you find I2 to be negative, that means that your assumption was not correct. If you assume the current in I and R2, for example, that's I2, that is as going down, and when you solve the equation and you find the value of I2 to be negative, that means that your assumption was not correct. The direction of the current in that resistor is up, not down. If you solve it and it comes out to be negative. So let's actually look on the equation that we have. I said, Khatar, I will get back to you. Just let me finish this. I1 at the junction, at that junction, IN, the incoming current, equals to the outgoing current. I1 equal to I2 plus I3. That's Kirchhoff's current law, KCL, Kirchhoff's current law. At loop number 1, E1 minus I R1 minus I R2 will equal to 0. That's Kirchhoff's voltage law for loop number 1. For loop number 2, where should I start? I started from I2 R2. So I started from here. I start from that point. In loop number 2, that's loop number 2. I started from that point. This is very good example in here. This is a good, guys, Hussein, focus and let go of the mobile. I'm going to go clockwise. But when I go clockwise, I'm surprised to find that the current is opposing to the direction I go. This, to me, is a negative current. So instead of saying it's a negative I2 R2, negative I2 R2, you put a negative current, you get a positive value. That's a common mistake. We all do in the exam under pressure, we miss that part. I choose to go counterclockwise, so I'm going to go from that point clockwise. I'm going to go from that point clockwise. So if you go up, you'll find that the current is opposing to your direction. That means that this is a negative current. So negative of negative, that will get I2 R2. Then if you continue, you get negative E2, you get negative I3 R3. This is Kirchhoff voltage law for the second loop. The third one, the big loop. The big loop. Which part? Okay. Let's do it on the board. Okay, Omar, I'm going to start from down there. Okay, Omar? Okay, now tell me what will be the drop in the potential across R2. Every time we have a resistor, there is a drop in the potential across that resistor. It's a negative I2 R2. But the direction of the current is in the opposite direction to your direction. So this is actually, it's a negative current. So you get negative I2 R2, but the current is always actually negative because it's in the opposite direction that the direction you're going through, then you get positive. Negative E2, negative I3 R3. That's equal to 0. Then you choose the big loop, the big one. What? Oh, again, this I1 is the current, the net current in that branch. It's not the current from E1. I3 is the net current in that branch. Net current in that branch. It's not the current from E2 or nor the current from E1. It's the resultant of the two of them. No, actually there is no direction in that case. We did not, when you apply Kirchhoff's current law at a junction, not at a loop. You do not choose a direction. You say that the current in equals the current out. Current into the junction, that's I1. Current out of the junction, that's I2 plus I3. This is the conservation of charges law.
So in equation 3, we ignored R2? We ignored the branch R2?
Question, I did not solve that yet. I did not get that yet. Okay, guys? Now, the big loop, the big one. I'll start, obviously I start up there. Oh, from E1. So E1, positive E1, negative I1 R1, negative E2, negative I3 R3, back to E1. So this is not part of the big loop. That branch is not part of the big loop. Okay? So now look at this. How many equations do we have? 4. More than we need actually. More than we need. We have 3 Kirchhoff's voltage law equations, 3 loops, and 1 junction equation, 1 Kirchhoff's current equation. We have 4 equations and 3 unknowns. I'm assuming that I know the values of E1, E2, R1, R2, and R3. Then simultaneously you can solve those equations. This is the hard part of that problem, of those kind of problems. The hard part of Kirchhoff's law is not actually applying Kirchhoff's current law nor applying Kirchhoff's voltage law. The thing that takes time, that consumes time in the exam, is to solve those equations together. Guys, no one can teach you how to solve them together, but practice. You have to solve many problems and get away how to solve the 3 equations together. But in the exam, if I ask you to find the value of I1, I2, and I3, and I give you that problem, if you give me the equations correctly, you get 8. If you solve the equations together and you get the correct values for I1, I2, and I3, you get 10. Oh. Okay, guys. So I'm sorry I will not be able to teach you how to solve the equations together. You have to practice. This is mainly practice. Say that again.
يعني
Amr.
there could be two currents going in opposite direction in the same branch at the same time.
Yes, and the net of them, I call it I2. The resultant of that, I call it I2, and I call it I3, and I call it I1. So again, I1, I3, I2, those are not the currents coming out from the batteries. Those are the net current in those branches. Thank you. Sure. It's coming. Don't look for it. So guys, in this problem, I actually continued on and I solved the equation. I'd really recommend that you try to solve them together without looking at the solution. Put the values. I put some numerical values in here. Put the numerical values and look at the values. But if you, after I assumed few numerical values, it happened to have I3 to be negative in my solution. What does that mean? It's in the opposite direction. I3 is going to be in that direction. Up. So not going to be down.
So Dr. I3 is that in opposite direction.
Mm-hmm.
Well, I1 is that كده I2 and I3.
No,
I1 و I3 يعني كده E2 أكبر من E1.
yeah. Let's say actually E2 is 12. What happens is the two batteries, they fire currents in those directions. And they go that way, and at that junction, the two currents splits. Some of them goes in here, and some of them goes there. That current goes out from E2, which is not I3. It's not I3. The current that goes out from E2, it goes up, and at the junction it splits down and to the left. The current that goes out from E1, which is not I1, it's not I1. It goes up, at the junction it splits to the right and down. And the resultant of those currents is I1, I2, and I3. Excuse me. Yeah. Yeah. Yes. Sorry.
When we solve the first one, the first circuit, we should take it clockwise, and the second one anti-clockwise.
No. Yeah, and this is what really happens. When I solve it any way I want, and if I'm correct, I will get positive values for the currents. If I'm wrong, I will get negative value for the current. But the magnitude of the current is going to be the same. It's not going to change.
What do E1 equal A2 plus I2 plus A3?
Yeah. Yes. Yeah. I1 equal to I2 plus I3, and again, this in that case. Yeah. Yes. In that case, I1 and I3 will be into the junction, and I2 is out of the junction. So actually, it's going to be I1 plus I3 equal to I2. Yeah. Okay, I'll go back to the problem that we were talking about. Guys, I have taught you now how to use Kirchhoff's voltage law and Kirchhoff's current law.
Dr. باش أعرف
Okay.
in Kirchhoff's voltage law,
Mm-hmm.
we assume in two loops are totally separated in
Yes.
يعني ازاي ان احنا بناخد لوب هنا مره اللوب ده مره واللوب كله مره وبنعمل نجلكت البرانش في النص ليه طب؟
Because I assume that the current I1, I2, and I3, my assumption is this is the net current in the branch. It's not the current that's coming out of the battery. As long as I did that, I'm okay. But if you want to complicate things, then if you want to complicate things, this is what you want to do. You say the current will go out from E1, I will call it I. I at that junction will split to I2 and I3. The current will go out from E2, I will call it I4. And I4 at that junction is going to split into I5 and I6. Good luck solving for I2, I1, I2, I3, I4, and 5, and I6. The other way to do it is to think a little bit wider and say, well, what happens is, at the end, from all those batteries, that branch will have a current I3. That branch will have a current I2. That branch will have a current I1. And it doesn't matter the direction. Even if you assume the direction wrongly, the answer will tell you that you have either you have got the right assumption or the wrong assumption. Okay? Okay. Oh, back to the problem that we were talking about. Guys, solve the problem. Now you know Kirchhoff's current law and Kirchhoff's voltage law. I want you to solve the problem the way you want. Assume whatever you want. As long as it's correctly, you get the same answer. I1 equal to I0. Don't at home assume that this is a very short assignment that's due Monday. Give it to me on Monday. And this will make you understand Kirchhoff's current law and Kirchhoff's voltage law. This is a good example to do this. This is a very short example that you have already the solution for. So Abdullah, do it and assume that a very short assignment. After the exam. Yeah. Okay, guys. So I'm gonna. I want, before we leave this part and go into connecting resistor and capacitor together, I want to revisit the power again. Our definition for the power, that's the energy per unit time. Our power as calculated for any circuit, that's the potential difference across any device times the current flowing in that device. This is the power. Now, if we are to have other formulas for the power equal to B IV. If you use Ohm's law, replace V, potential, by IR, then the power is given by I square over R, or the power can given to be V square over R. Those are three formulas for the power that we have studied before. Now, if I want to transmit power from the high dam to Cairo, what should I do? Should I put high potential or should I put high current? Should I use transmit it through high current or high potential? So let's look at this. For any device in the whole universe, what's important is the efficiency. How much power you put in and how much power you get out. Any device, even human being. You eat, you take power in, then you exert energy, you get power out. The efficiency of any device, that's the important thing that we measure the capability of that device by. So transmission lines are just devices. I want to measure the efficiency of the transmission lines. So efficiency by definition is P out divided by Pn. The power out divided by the power in. Power out, it's the power N minus the losses. It's the power you put in on the transmission line minus whatever you lose in the transmission line. If the losses is zero, then you get 100% efficiency, right? And that's what we want. We want to use a superconductor material that has a zero resistance in order to minimize the losses. So this is the definition of the power. IVN minus I square R, or IVN, this is the definition of the power for the transmission line. IVN divided by IVN, that gives you 1. I square R divided by IVN will give you, oh, this is the current, this is the power drawn by any resistor, and a wire is a resistor. This is the power drawn by any resistor. It's I square R. It's the current in that resistor times R. That's lost. And you feel it as heat. If you hold any wire covered by plastic or something, then you feel it, it's going to be hot. Your computer gets hot all the time by the current that flows in it. And this is mainly I square R.
IR.
That's the potential drop, not the power.
إذا ضغط الكوندكتور برضه current will flow and مش will heat up.
Oh, but if the resistance is zero, then there's no resistance, nothing will heat. If you move your hand on the table, because there is resistance by friction, you feel the heat. But if there is no friction, if you move your hand on something that is very smooth, then you will not feel heat. So again, this is the power out. It's the power n minus the losses divided by the power n. So if you divide this by this, you get 1 I square r over I v n. You get I square r. When you were sleeping, we were saying P out over P n, that's the efficiency.
بتكلم عن الكالكوليشن ازاي اي بي ان تعمل على ديفايس اي بي.
Okay, that's a good question then. My son, who's 10 years old, knows how to do this. I v n minus I squared r divided by I v n equals I v n divided by I v n minus I squared r divided by I v n. I hope that you agree that this is 1. Thank you. Then, guys, you're going to be the engineer of the future. Come on. Okay, then, then, IR over Vn. Okay? IR over Vn. Then I will multiply by 1. By 1. To deliver a point. I will tell you what is that point in a minute. Okay? So it's IR times Vn divided by Vn divided by Vn. This is 1 minus I times Vn. What's I times Vn? Power. Power in. Times R divided by Vn. Wait. What's Vnr? Oh, yes, squared. Good. Now, this is the equation for the efficiency then. It's 1 minus Pn divided by times R divided by V square n. Look at that equation and examine it carefully and tell us what do we really need to transmit the power. We need to lower the resistance, use superconducting material, but we need to use very high potential. If you use high potential, you minimize that term. You increase the efficiency. That's why it's very important that we transmit the power across high potential, not across high current. Okay, guys? So again, this equation, it describes to you the efficiency of the transmission line from any power station to the consumer in Cairo, Aswan, and whatever the place is. Kareem.
Yeah, VN هنا الفولتج بتاعنا. الانبوت يعني.
Yes, input voltage.
الفولتج difference between the input and the output.
It's the input voltage.
طب الانبوت فولتج ده عبارة عن ايه؟ يعني ده difference
between the N and the 0. You ground the line. You have a ground in that line. So this equation tells you that we really need a superconductor, but that's not much as we need to transmit that as a high potential. So this is the power transmission and the efficiency of the power transmission, and we know. Sure.
In this equation, we need to higher the voltage عشان يبقى better efficiency, better power out.
Yeah.
But that, لو طب حضرتك تقول current, احنا we don't have to increase the current to have a better power out. But that contradicts the equation of power اللي بتطلع حضرتك في السلايد اللي قبليه. يعني اللي هو ال power equal I squared R. لما هتلاقينا لو زودت الكرنت
The B consumed in the wire. The B the power lost in the wire. The power lost in the device that has a resistor R. You increase the current, you increase the losses, the power lost.
From here also you increase the voltage, you increase the power loss.
Yeah, yeah, true, true, but here we're talking about efficiency. The power loss is going to be the same, but actually what you do is the power loss is going to be minimized if you increase the power. You forgot here about when you increase the power, the V, you have R as well working with you, to opposite that. So this is 1 minus, this whole term is the losses. This whole term is the loss. Actually, if you increase the Pn, the power N, you increase the losses. But if you have power N that's fixed, resistance that's fixed, is it better for you to transmit the power across 100 volt or 1000 volt?
الافشنسي هتزيد بس برضه في نفس الوقت اللوسز هي
Yeah, but the efficiency is the same because if you increasing the power N in that case. So guys, this is Kirchhoff's current and voltage law. So far we talked about how to connect resistors together, how to connect capacitor together. Now this is the time to connect capacitor to a resistor together. And this is, I'm not going to teach you the equation now, but let's think about the physics today. And on next not that Saturday, the day after, we'll talk about how actually to derive that equations. There is no class, there is an exam on Monday and there is no class on Thursday. Yeah. So this is a resistor connected to a capacitor together. Guys, this is a resistor, Omar, a resistor connected to a capacitor together. What happens in that circuit? What happens in that circuit? I'm going to assume that, okay. So if you have the switch is open, if you have an open switch, that's the switch, they're up there, if you have that switch open, so there is no current in here. Once you switch the switch on, what happens? What happens? Charge will flow, right? What could drop in the potential across that, and what happens across the capacitor? What is the potential? Exactly after you switch the switch on, what will be the potential across the capacitor? Yes, Q over C. What is the charge across? What's C? What is the capacitance? What does the capacitance depend on?
Is it going to be E minus?
I'm asking something. It's geometry. So C is constant. It depends only on the geometry of the capacitor. So what is that? What will be the charge on the capacitor once you switch the switch on? 0. And if you have 0 charge on the capacitor, what will be the potential on the capacitor? 0. So the potential difference across those two capacitors once you switch the switch on is 0. The capacitor will act like what? Battery? Oh, well, you said battery. If it acts like a battery, battery has a potential difference across it. This has 0 potential across it. So it's not a battery. Guys, you're answering something that I did not ask. I'm asking, once you switch the switch on, no charge will be on the capacitor. The voltage across the capacitor, across those two plates is going to be 0. There is no potential across them. This will act like something. And Kareem said it's going to act like a battery, and I told him no, it's not going to act like a battery because the battery has a potential between the two terminals. Thank you. This is going to be an equipotential surface. What's an equipotential surface? Someone said a wire in here. Yes, wire. So at the beginning, at time equal to 0, once you switch the switch on, this will act like a wire. The circuit will be like just the battery and the resistor. Then what happens after that? Charge will start to accumulate on the two plates. This will be fully charged. It will be fully charged in such a way that the potential across it equals the potential across the battery, and no current will flow. And in that case, the capacitor will act like an open switch. If this is a circuit, just a circuit without the capacitor, and you open a switch in here, there will be no current flow. So the capacitor will act like an open switch. So now we know the extreme cases. We know what happens at the beginning when we switch the switch on, and we know what happens after a very long time. At the beginning, this will act like a wire, just a wire. After a very long time, the capacitor will act like a switch, open switch. And between them, there's something happen. Between those two extremes, the charge will accumulate on the capacitor. And if we want to find out what will be the charge as a function of time, this is going to be the topic of next lecture. Khatir, what did he say?
Charges takes a long time.
Yes, the charge will take a time to fully charge the capacitor, and we need to know how long it will take. We'll find out.
Yeah, when the charge accumulates on C,
Guys, we did not finish yet. Kareem.
V equal to E?
Yes.
Subject.
We'll see. Equation. We'll see about the equation in a minute. Actually, next lecture.
And voltage across the capacitor will be E minus I for R.
Excuse me.
The voltage across the capacitor will be E minus I for R.
Across. Yes, it's E minus IR. Yes. Abdullah is saying, well, can we apply Kirchhoff's voltage law on that circuit? Yes. It's E minus IR minus the potential across the capacitor equal to 0, which means that the potential across the capacitor equal to E minus IR. At any time. That's it. At any time. The potential across the capacitor equal to E minus IR. But what's important today is to know what happens at the two extremes. At time equal to 0, once we switch the switch on, and at time equal to infinity, after a very long time, and having the switches on, before we leave. Now assume that suddenly, after charging the capacitor, I took the battery out, and connect that by a wire. What happens? At time equal to 0, at that time, the capacitor will act like a battery. After a very long time, it's an open switch. Actually, after a long time, all the energy that we have stored in the capacitor will be consumed by the resistor. And those two cases, charging and discharging the capacitor, this is the topic of the next lecture. We'll study mathematically how to find the equation that describe those acts. Khatir, before we leave, last question.
If you started with a discharge capacitor.
Oh, there's no, if you start with a capacitor does not have any energy, then nothing happens. Yes, we assume that it's fully charged before we take the battery out and connect it by a wire. Okay, guys. So you remember there is an assignment